Welcome back, design junkies. You have power over your calculations, not over reality. Control what you can, respect what you can't.
That is quite the heavy thought to kick us off today.
I mean, it really sets the tone, right? Because today on the deep dive, we are getting into some incredibly high stakes. So imagine a microscopic scratch on the inside of a stainless steel pipe.
Okay, I'm picturing.
Like maybe it's 1.8 microns deep, which, to put that in perspective, is totally invisible to the naked eye. It's just a fraction of the width of a human hair.
Barely even a texture.
Exactly. So to the machinist who polished that pipe, it looks like a perfect mirror-like surface. But to a Listeria bacterium.
Oh, to them, that 1.8 micron scratch is basically the Grand Canyon.
Yeah, it's a vast protective valley. They can just hunker down in there, multiply, and actually survive the onslaught of boiling industrial cleaning chemicals.
And that right there is how you eventually trigger a multi-million unit product recall.
Right. And that's exactly our mission today. We are looking at the direct pipeline between the theoretical world of an engineer's CAD software and that microscopic bacterium hiding on the factory floor.
It's a huge transition. Going from the drafting table to the actual manufacturing floor is probably the most brutal reality check any student engineer will ever face.
Because in the digital space, everything is flawless.
Exactly. A line is perfectly straight. A curve is mathematically tangential. But the moment you hand that blueprint to a fabricator, you're not dealing with geometry anymore. You're dealing with physics and chemistry and, frankly, human interpretation.
Human error, really. And we are specifically looking at this through the lens of sanitary food equipment design, the machinery making the poultry, the dairy, the baked goods you and I eat every day.
Which is a highly regulated environment. An engineering drawing isn't a suggestion in this field. It's a binding legal contract with reality. There is zero room for error.
And that brings us to the core conflict we are unpacking today for all you student engineers out there stepping into your careers. In school, a mislabeled drawing means you get a docked grade.
A B- instead of an A.
Right. But in the real world, an engineer might use an ambiguous piece of shorthand just because they are, trying to save space in a tiny text box on their screen.
Which happens all the time. But then the welder on the floor misinterprets that shorthand. Maybe they use a slightly different filler metal based on that guess.
And suddenly you've got a microscopic pocket of corrosion.
Yeah, and that corrosion becomes a microbial growth niche.
All because of a single ambiguous letter on a blueprint. It's wild. We tend to think of abbreviations as simple conveniences, right? Just shorthand to keep our wrists from cramping.
But the reality is that the governing standards dictate a literal gauntlet. Any new abbreviation has to survive this intense criteria before it is allowed anywhere near an official blueprint.
Okay, let's unpack this gauntlet. Because the barrier to entry sounds intentionally massive.
Oh, it is. You absolutely cannot just decide that typing out a word is tedious and invent your own code. That's rule number one.
So what's the very first hurdle a new abbreviation has to clear?
It has to prove a genuine, demonstrated need. The governing bodies basically demand proof that spelling the full word out is actively hindering the mechanical drafting process.
Meaning you just don't have the physical space on the page.
Exactly. It almost exclusively boils down to severe physical space constraints on the drawing itself.
So if I just feel like shortening the word bracket to BRK because, I don't know, I'm typing it 50 times a day.
If you have plenty of white space on that page, it gets rejected immediately. Out of hand.
Wow. Okay, but let's say I do have a legitimate space constraint. A really dense schematic.
Even then, the word itself has to qualify. And the second rule is strict. The original term must be at least 5 letters long.
Wait, really? 5 letters?
Yep. 4-letter words or anything shorter are entirely disqualified from being abbreviated, period.
I really want to push back on that 5-letter rule. My instinct as an engineer is to optimize everything, right?
Sure, optimization is the goal.
So if physical space on a drawing is at an ultimate premium, and that is the whole justification for abbreviating in the first place, why restrict a 4-letter word?
I see where you're going with this.
Right. If I have a 4-letter word and I reduce it to 3 letters, I've technically reduced the required spatial footprint by 25%. In a highly dense diagram, every single millimeter counts.
Well, you are looking at the optimization strictly from a spatial perspective. But the standards are actually optimizing for human cognitive load.
Cognitive load, how do I mean?
Think about the reader. While you save a single character space by shortening a 4-letter word to 3, the actual physical real estate gained is virtually microscopic.
Yeah, I guess that's true. It's just 1 letter.
But you have just drastically altered the visual processing required to understand that note. When a human rods a familiar word, they don't sound out individual letters.
Right, they see the shape of it.
Exactly. Their brain recognizes the overall shape of the word in a single rapid eye movement, a saccade. But by changing the word into an abbreviation, you force the reader's brain to stop.
Oh, I see. They have to recognize the text as a coded symbol.
Yes, and then retrieve the cipher from their memory and decode it back into the original concept. The friction of decoding entirely outweighs the tiny bit of physical space you saved.
That makes a lot of sense. You're trading a millimeter of paper for a mental roadblock.
And consider who is actually decoding this document. The engineer who drafted it knows exactly what they meant. But 6 months later, it's a third-shift machinist reading it under poor lighting.
Or a purchasing agent.
Right, a purchasing agent with a business degree, not an engineering degree, looking at the bill of materials.
Oh.
Or, years down the line, a regulatory auditor checking the maintenance logs.
So if you introduce a decoding step for a negligible spatial game, you're exponentially increasing the probability that someone is going to guess wrong.
Precisely. The foundational doctrine here is that clarity unconditionally supersedes brevity. If there is even a fractional % chance of ambiguity, the golden rule is simple. You spell the word out entirely.
Okay, that totally reframes the concept for me. The abbreviation isn't a tool for the writer at all. It's a calculated risk for the reader.
That is exactly the right way to look at it.
Now, what about the other rules? We have the space constraint, the 5-letter minimum. What else?
The proposed shorthand cannot contain any subscripts or superscripts. It must be rendered in completely clean, plain text.
Keeping it simple so software or different printers don't mess it up, I assume.
Absolutely. Furthermore, it cannot duplicate an abbreviation that has already been established in the standards.
That seems like common sense, but I imagine it's hard to avoid.
It's critical, though. We cannot have a scenario where CMP means compressor to a mechanical engineer, but it means compound to a chemical engineer who happens to be reading the exact same diagram.
Oh, man. That would be a disaster.
And finally, the term must have widespread, universal application. Highly localized jargon that's only utilized by a single subdepartment in one specific factory does not qualify for standardization.
So it has to be a universal language. Okay, let's assume an abbreviation actually survives this gauntlet. It represents a long-term, no conflicts. It enters the official lexicon. Language in the real world is incredibly dynamic, you know.
It is. It's constantly shifting.
We conjugate verbs, we pluralize things. How does a highly rigid, standardized code handle the organic complexities of grammar? Like, do we just add an "es" to an abbreviation if we have multiple components?
You absolutely do not. The standardized system handles the grammatical complexity by outright refusing to participate in it.
Really? They just ignore grammar?
Pretty much. Technical abbreviations operate less like a spoken language and more like modular, immutable building blocks.
Yeah.
The syntax rules are draconian, specifically to prevent organic variation from slowly diluting the meaning.
So how does that work in practice?
Unless an explicit exception is carved out, you use the exact same abbreviation for the singular, the plural, the possessive case, all participle endings, and every conceivable verb tense.
I'm trying to picture this in my CAD software. So if I look up the official abbreviation for the word calculate, which I think is calc, just C-A-L-C.
That's correct.
Am I locked into using it just as a noun, like a calculation, or does that exact block of 4 letters cover me if I need to instruct the machinist to calculate something, or note that a tolerance was calculated previously?
It covers all of the above, without a single alteration to the letters. Calc stands in for calculate, calculated, calculating, and calculation.
So you don't append an "es" for plural or an "ed" for past tense?
Never. The block remains calc. The reader determines the tense and the part of speech entirely through the contextual syntax of the surrounding note.
It just strips away all the inflection. But what happens when we start dealing with established phrases? Engineering is full of composite phrases.
This is where the rules become even more inflexible. If a standardized abbreviation exists for a specific multi-word phrase, you are strictly forbidden from dismantling it to use its component parts.
Give me an example of that.
Consider the abbreviation for stainless steel. The official approved shorthand is SST. The standard explicitly prohibits reverse engineering that combination.
So I can't look at SST and extrapolate that S must mean stainless and STL must mean steel.
Exactly. You cannot do that. If you are drafting a note and you need an abbreviation for just the word steel on its own, you must go back to the standard and find the specific standalone code for that single word. The combinations are entirely locked.
But engineering is constantly evolving, right? We invent new processes, new materials, new composite phrases every day.
We do.
If I have these immutable building blocks, but I need to dictate a brand new phrase on a drawing, something the standards committee hasn't even addressed yet, how do I build it without breaking the rules?
You build it modularly, using only the approved standalone blocks. Let's say you need to specify an average temperature on a thermal schematic.
Okay.
And you consult the standard only to find that average temperature has no official unified abbreviation. You have to instruct it yourself.
Yeah.
You pull the approved code for average, which is AVG.
Got it.
Then you pull the approved code for temperature, which is TEMP, and you simply place them side by side with a space, resulting in AVG space TEMP.
It functions exactly like root words and prefixes. I noticed this logic with the word cathode, actually.
Oh yeah, that's a perfect example.
If you are using the term cathode as a standalone noun, the abbreviation is CATH. But the moment you use it as a combining form, like a prefix to modify another concept, it reduces down to just the letter C.
Right. So when you build cathode ray tube,
It becomes CRT. It is an incredibly elegant modular architecture.
and that modularity is the only mechanism preventing the entire documentation system from collapsing under the weight of infinite variations, because the assembly rules are perfectly rigid.
It means anyone can understand it.
Exactly. A fabricator in Germany and an inspector in Ohio can both encounter a completely novel, multi-word abbreviation they have never seen before. But by breaking it down into its constituent standardized blocks, they arrive at the exact same technical conclusion with zero ambiguity.
All right, so we have established the grammar of the blueprint. We know how the ink gets placed on the page. Now let's talk about what happens when that ink translates into cold, hard steel.
This is where things get serious.
Yeah, this is where the stakes escalate dramatically, specifically in the realm of food processing equipment. The drawing is no longer just a set of instructions. It is quite literally a primary defense mechanism against biological contamination.
The shift from abstract communication to physical consequence is severe here. In the food manufacturing industry, the overarching foundational doctrine is that the processing equipment itself must never become a vector for contamination.
Right, from the moment raw poultry enters a facility to the moment a baked good is sealed in plastic, every conveyor belt, every slicing blade, every vat is a critical control point.
Because the machinery is in constant contact with biological material that is highly susceptible to rapid bacterial proliferation.
So when we look at how contamination physically occurs on a machine, we have two distinct vectors: transfer points and microbial growth niches. Let's start with the transfer points, because those seem fairly intuitive to me.
They are. Transfer points are the inevitable, engineered points of contact. They were the primary product contact surfaces.
Like the inside of the pipe carrying raw milk, or the mechanical dough kneader.
Exactly.
Right.
Cross-contamination at these points is a guaranteed known risk. Because we know they get dirty, the industry manages them through good manufacturing practices and rigorous standard operating procedures for cleaning.
So it's handled operationally.
Yes. Production runs for a specified duration,
Sure.
the line halts, the sanitation crew moves in with foaming agents and scrubbers, and the transfer points are neutralized. They are visible, they are accessible, and they are entirely expected.
It's the equivalent of washing a dinner plate after a meal. Touch the food, you see the residue, you apply soap, and the risk is eliminated.
Perfect analogy. But the second vector, the microbial growth niche, operates entirely differently. This is the phenomena that keeps plant managers awake at night.
And this is the direct consequence of poor engineering on the blueprint, right?
Absolutely. A growth niche is essentially an architectural failure on a microscopic scale. Yeah. It is an unintended sanctuary within the geometry of the equipment.
We are talking about microscopic pits in a metal finish.
Or a hairline crack in a weld. A poorly sealed recess behind a bolt head. Or even a tiny hollow chamber where moisture and organic product can accumulate out of sight.
And because they are out of sight, the standard cleaning protocols just don't touch them.
That is the terrifying reality. These niches create environments that are impervious to the daily sanitation cycles. Microorganisms like Salmonella, Campylobacter, and Listeria monocytogenes migrate into these recesses.
And they don't just survive in there, do they?
No, they thrive. They establish complex biological communities called biofilms. These biofilms excrete protective polymeric substances that act as a physical shield.
Wow, so they build their own armor.
They literally do. This shield repels the chemical sanitizers being sprayed over the surface of the machine. The bacteria multiply within this fortress, and as the colony grows, it periodically sheds pathogens back out onto the passing food product.
It becomes an invisible, perpetual engine of contamination.
It really does.
I think of it like a cavity developing underneath a dental filling. If the dentist leaves a microscopic void between the tooth and the resin, it does not matter how obsessively you brush your teeth.
You're only cleaning the surface.
Exactly.
Yeah.
You can use the most expensive electric toothbrush and the harshest mouthwash on the market. But deep inside the void, the bacteria are perfectly protected. The rot continues to hollow out the tooth, completely unaffected by your daily sanitation routine until the underlying architecture collapses.
That analogy is perfectly accurate. The sanitation crew in a food plant is the toothbrush. Their effectiveness is strictly limited by the geometry of the surfaces they are cleaning.
And the engineer drafting the blueprint is the dentist.
Yes. They are the only line of defense against the creation of those cavities. If an engineer specifies a porous material, or dictates an inadequate corner radius, or uses a vague abbreviation that leads a fabricator to leave a rough, unfinished seam, they have successfully engineered a bacterial fortress.
A $50 million food processing facility relies entirely on the architectural geometry dictated by the abbreviations on that CAD file. That is a crazy amount of pressure on a drafting note.
Which brings us to the actual vocabulary of cleanability. To prevent these niches from ever existing, an engineer cannot just draw the shape of a machine. They have to explicitly codify exactly how every square inch of that machine will be accessed and maintained by the cleaning crew.
And the standards define very specific terminology for this. Let's look at access first. The blueprints will categorize parts as either accessible or readily accessible.
Right.
Now, to a layman, those sound like synonyms. From an engineering perspective, what is the critical distinction?
The distinction dictates the mechanical design of the closures, and it ultimately boils down to the use of tools.
Tools.
If an engineer designates a component or an internal chamber as accessible, it legally implies that the area can be exposed for inspection and sanitation. But the operator may be required to utilize simple hand tools to achieve that exposure.
So what counts as a simple hand tool?
The standards explicitly define them as implements normally available to operating personnel. So a standard wrench, a screwdriver, or perhaps a dedicated mallet for knocking loose a fitting.
Okay, so if I design an inspection hatch that is secured by 6 hex bolts, that satisfies the requirement for accessible.
It does. However, if the drawing dictates that the chamber must be readily accessible, the engineering constraints become significantly tighter.
No tools allowed?
0. That designation mandates that the surface must be easily and swiftly exposed for inspection and cleaning entirely without the use of any tools whatsoever.
So the hex bolts are out. I have to engineer a hinged access door with a quick-release cam latch or some kind of toolless clamp system.
Correct. And the engineer must make this calculation based on the required frequency of sanitation and, importantly, the human element of fatigue.
Oh, that makes sense. If you have to take off 20 bolts every single shift.
Exactly. If you have a critical internal surface that requires heavy physical scrubbing every shift, and you design it as simply accessible with 20 bolts holding the cover panel on, human nature and time constraints guarantee that eventually a fatigued worker will stop unbolting that panel.
They'll just skip it.
They will. The readily accessible designation forces the engineer to build inherent, frictionless compliance directly into the physical machinery.
Fascinating. So once we can access the equipment, we have to instruct the facility on how to actually clean it. And the abbreviations for these protocols are industry bedrocks. We're talking about CIP, COP, and IPC. Let's dismantle these, starting with CIP.
CIP stands for Clean in Place. And I want to stress, this is not just a procedure, it is a highly complex engineered fluid dynamic system.
What does it actually entail?
When a pipeline or a vat is designated CIP, it means the internal product contact surfaces will be cleansed of soil by circulating, flowing, or spraying chemical solutions and water rinses without dismantling any part of the system.
So the equipment functions as a sealed, pressurized circuit.
Exactly.
And the physical forces at play here must be intense, right? You aren't just letting soapy water soak inside a pipe.
Far from it. CIP relies heavily on mechanical shear force generated by turbulent fluid flow.
Shear force?
Yes. The system must be engineered to pump the chemical sanitizers at velocities high enough to achieve a specific Reynolds number. This ensures the flow is highly turbulent rather than laminar.
So it's not a smooth flow, it's chaotic and aggressive.
Very aggressive. This turbulent action literally tears the bacterial biofilms off the internal walls of the pipe, while the heat and the chemical alkalinity destroy the cellular structures. It is a violent, highly controlled internal scouring process.
Wow. Okay, contrast that with COP.
COP is cleaning out of place. This protocol is assigned to complex components that cannot be engineered to withstand or properly circulate CIP fluids while remaining in their process position.
Like what kind of parts?
Consider the complex multi-vaned impeller of a high-viscosity pump, or a delicate manifold with multiple intersecting channels.
The fluid dynamics wouldn't work right in those shapes.
Exactly. So the blueprint dictates that these parts must be physically removed from the assembly by an operator and transported to a dedicated remote sanitation room.
And how are they cleaned there?
There, they are typically submerged in specialized turbulent washing vats that ensure the chemicals penetrate every complex geometric recess.
Got it. And finally, we have IPC, in-place cleaning. This seems like a broader category to me. The guidelines detail mechanical dry cleaning, which covers using compressed air or industrial vacuums to remove dry soils like flour dust in a baking facility.
Right, that's one aspect.
But the other subcategory under IPC is wash-down design. Now, I need to push back on this because logically, I'm struggling to see the distinction.
Let's hear it.
If a machine is designated for washdown, that means it stays exactly where it is, and a sanitation worker hits it with water and industrial foaming chemicals to remove the soil. You are cleaning the machine in place. Why is washdown not simply categorized as CIP?
That is an incredibly common misconception, and it's a dangerous one. Confusing those two abbreviations on a blueprint is a direct path to a catastrophic sanitation failure.
Really? How so?
You are conflating the physical location of the equipment with the fluid dynamics of the cleaning process. CIP, as we established, is an internal, closed-loop operation.
Right.
The machine is designed to contain high-pressure, high-velocity, highly caustic fluids circulating through its own internal plumbing.
It's acting as its own washing machine.
Exactly. Washdown design, conversely, applies exclusively to the exterior architecture of stationary equipment.
Ah, the exterior.
Yes. It indicates that the machine's external housing, its motors, its electrical enclosures, and its structural frame have been engineered to be hermetically sealed against moisture ingress.
So a guy in rubber boots can just hose it off.
Exactly. It allows an operator to walk up to the machine with a low-pressure hose and manually spray the exterior surfaces with mild detergents and water without short-circuiting the electronics or destroying the mechanical bearings.
Okay, the distinction is internal closed loop versus external manual application. But let's say I'm a junior engineer and I accidentally label an internal fluid manifold as washdown instead of CIP on the drawing. What is the actual physical consequence of that typo?
The consequence is that the fabricator builds the manifold without accounting for the internal fluid dynamics required for CIP.
So what changes physically?
They might use pipe diameters that are too wide. That drops the fluid velocity, preventing the turbulent flow necessary to shear off biofilms. They might include sharp internal angles where fluid velocity drops to zero, creating dead zones.
Oh man, so the pipes literally won't flow fast enough to clean themselves?
Exactly. When the plant attempts to run a CIP cycle through that manifold, the chemicals will merely trickle over the bacterial colonies without dislodging them.
Leaving the biofilms completely intact.
Biofilms will thrive, protected by the very geometry of the pipe. Your entire production line becomes a continuous microbial generation system, all because the wrong abbreviation dictated the wrong engineering intent.
That is a staggering chain of causality. A 3-letter code alters the fluid dynamics, which protects the biofilm, which ultimately taints the product.
It all starts with the blueprint.
Which directly segues into our next layer of engineering, the materials themselves. Because you cannot dictate how to clean a machine if the metal itself is fundamentally incompatible with the environment.
No, you cannot.
The engineering standards divide every machine into 2 distinct territories, the product zone and the non-product zone.
This division is the absolute bedrock of sanitary material science.
So define the product zone for me.
The product zone encompasses all surfaces that the food product or any of its ingredients will normally come into direct contact with. However, the definition extends much further than that.
How far?
The product zone strictly includes any adjacent surface from which condensation, splash liquids, or foreign material could potentially drip, drop, or be drawn back into the main product stream.
Oh, wow. So if I have a massive open-top mixing vat for liquid dairy, the structural ceiling located 3 feet above that vat, that is legally classified as the product zone, even though the dairy never physically touches it.
Precisely. Because steam rising from the vat will condense on that ceiling. If that ceiling harbors bacteria, the contaminated condensation will rain directly back down into the open vat.
That makes total sense, but it really expands the footprint of what you have to worry about.
It does. Therefore, the sealing must adhere to the exact same stringent material requirements as the mixing blades themselves.
And what are those requirements?
They are absolute.
Mm.
Any material in the product zone must be non-toxic, non-absorbent, and entirely resistant to both the product chemistry and the highly corrosive cleaning chemicals.
To enforce this, the standards provide a literal do-not-fly list of completely banned materials. And what is fascinating here is the specific physics and chemistry behind why these materials failed the test. For instance, wood is universally banned across the board.
Wood is the ultimate architectural failure in a sanitary environment because it is inherently and irreversibly porous.
I mean, it's a plant.
Right. At a microscopic level, wood is a bundle of cellulose tubes designed by nature to transport water. Once biological fluids, fats, or moisture enter the grain of the wood, it is physically impossible to sanitize it.
Because the cleaners just can't soak in deep enough.
Exactly. The chemicals cannot penetrate deep enough to eradicate the bacteria harboring inside the cellular structure of the timber.
Okay, what about enamelware? That's also completely banned. Now, enamel is essentially glass fused to metal. It's incredibly smooth. Why is it disqualified?
While it possesses excellent surface smoothness, enamel is structurally brittle.
Ah, so it ships.
Yes. In a heavy industrial environment experiencing extreme thermal cycling from CIP processes and mechanical impacts from tools and vibration, enamel will inevitably microfracture and chip.
And that chip ruins the whole thing.
A single tiny chip destroys the integrity of the surface. It instantly creates an impossible-to-clean crevice that simultaneously exposes the reactive base metal beneath the enamel to corrosive fluids.
That brings up aluminum. Uncoated aluminum and anodized aluminum are explicitly banned from the product zone as well. This seems counterintuitive because aluminum is used everywhere in commercial kitchens. Pots, pans, baking sheets.
It is acceptable in light commercial settings, but industrial food processing relies on incredibly harsh cleaning agents to dissolve organic soils.
Like what?
The most common CIP chemical is sodium hydroxide, which is a highly alkaline caustic soda. Aluminum is highly reactive to alkaline solutions.
So what happens when they mix?
When sodium hydroxide hits uncoated aluminum, it violently strips away the natural protective oxide layer and begins to dissolve the base metal.
It literally eats the metal away.
It does, and it doesn't do it evenly. It creates a severely pitted, microscopic lunar landscape on the surface of the aluminum. What was once a smooth part becomes a vast, porous sponge of deep craters. It turns the entire component into one massive, inescapable growth niche for pathogens.
Okay, so that's a hard no on aluminum. We also see total bans on heavy metals, lead, antimony, cadmium, which is entirely logical from a basic human toxicity standpoint. Tin alloy solder is also outlawed, but the rules that truly demonstrate the complexity of food engineering are the conditional bans.
The conditional bans are where you really have to know your chemistry.
Right. Copper, brass, and monoll, which is a high-performance nickel-copper alloy. The guidelines explicitly state you cannot specify these metals if they will interact with fatty foods. Edible oils, liquid shortening, chocolate liquor. Why does the chemistry of fat specifically outlaw copper?
This is a perfect example of metallurgical chemistry colliding with food science. Copper and its various alloys act as aggressive pro-oxidant catalysts when they come into contact with lipids, which are fats.
Pro-oxidant, so it makes them oxidize faster.
Exactly. At a molecular level, the surface of the copper facilitates a rapid transfer of electrons. This initiates a free radical chain reaction within the fat molecules.
It drastically accelerates the oxidation process.
It does. And this oxidation immediately breaks down the lipid structures, leading to rapid, severe rancidity.
Oh, gross.
The product develops off flavors, foul odors, and degrades nutritionally within minutes of contact.
So an engineer drafting a schematic for a dry flour milling system might freely specify brass fittings without any issue at all.
Correct, because there are no fats involved.
But if that same engineer is transferred to a project designing a chocolate enrobing line, and they just copy-paste that same brass fitting schematic,
they will chemically destroy thousands of gallons of chocolate liquor before the product even leaves the factory. The material must perfectly match the molecular reality of the product.
Adding to that complexity, these materials do not exist in isolation. You have to bolt them, weld them, and join them together to actually build the machine. And this introduces a phenomenon that I find absolutely fascinating: galvanic corrosion. The baking standards explicitly mandate that dissimilar materials shall not be used where electrolytic corrosion may take place.
This is where basic physics creates a biological nightmare. Galvanic or electrolytic corrosion occurs when you place two electrochemically dissimilar metals in direct physical contact and then introduce an electrolyte.
And in a food processing plant, the electrolyte isn't a battery acid. It's the highly conductive cleaning chemicals, or even the salty food product itself, bridging the gap between the two metals.
Exactly. When the electrolyte bridges the two dissimilar metals, it creates a microscopic galvanic cell, a literal battery.
Wow.
One metal, the more noble one, acts as the cathode. The less noble metal becomes the anode. The electrolyte facilitates the migration of electrons from the anode to the cathode.
And what's the physical result of that?
In doing so, the anode metal sacrifices itself. It literally dissolves at the point of contact.
Let's walk through a real-world scenario so people can visualize this. Let's say an engineer specifies a food-safe aluminum bracket and attaches it to a food-safe stainless steel structural frame using stainless steel bolts. Both materials are technically food-grade on their own, right?
On their own, yes, perfectly safe. But the moment the sanitation crew sprays that joint with a conductive foaming cleaner, the aluminum becomes the anode and the stainless steel becomes the cathode.
And the battery is turned on.
The battery is on. The aluminum immediately surrounding the threads of that stainless steel bolt begins to electrochemically dissolve.
And as it dissolves, the tight physical tolerance of that joint is destroyed. A gap that was microscopically tight yesterday is now 5 microns wide.
And the bolt loosens slightly, allowing moisture and organic matter to seep into the newly formed void.
So the engineer, by failing to account for electrochemical compatibility, has used two perfectly safe materials to inadvertently build a deteriorating microscopic cavern where listeria can thrive, completely shielded from the daily cleaning cycle.
That is exactly what happens.
Which brings us down to the absolute atomic level of the blueprint, the microarchitecture. When an engineer dictates a material, merely typing SST for stainless steel is vastly insufficient. They must codify the exact geometric topography of the metal's surface. Let's analyze surface roughness. The guidelines demand numerical values that are almost difficult to conceptualize.
The required tolerances are staggering, especially if you are accustomed to standard industrial manufacturing.
Give us numbers.
For equipment processing meat and poultry, the microscopic texture of a product contact surface cannot exceed 32 microns in roughness. As we mentioned earlier, a single human hair ranges from 70 to 100 microns in thickness.
So the absolute deepest microscopic valley in the metal has to be less than half the width of a hair. And for highly perishable, high-risk fluids, the constraints tighten exponentially. The standards for dairy or liquid egg processing systems mandate a surface equivalent to a number 4 mil finish on stainless steel. In measurable terms, that translates to an arithmetic average roughness, or RAW, of no greater than 1.8 microns.
1.8 microns.
That is essentially an optical mirror finish. Why is it necessary to polish steel to a mirror finish just to pump milk through it?
Because of the physical scale of the enemy. A single bacterial cell is typically between 1 and 2 microns in length.
Okay.
If the microscopic polishing grooves in the steel are 3 or 4 microns deep, the bacteria will settle into those valleys.
They just tuck themselves in.
Yes. When the highly pressurized CIP cleaning fluid rushes through the pipe, the fluid dynamics dictate that the velocity drops to near zero inside those microscopic valleys.
Oh, I see.
The turbulent shear force simply glides right over the top of the grooves, leaving the bacteria nestled safely below the current, entirely untouched.
So the 1.8 micron requirement.
An arithmetic average of 1.8 microns ensures that the architectural valleys are physically smaller than the bacteria. The microorganisms have nowhere to retreat. They are forced to remain exposed on the upper topography of the metal, where the fluid shear forces can physically rip them away.
That is incredible. And to highlight the contrast, the non-product contact surfaces, like the exterior structural legs of the machine, they are permitted a roughness of up to 125 microns. The engineering precision and the extreme manufacturing costs required to achieve that 1.8 micron finish is laser-focused exclusively on the biological front lines of the product zone.
Exactly. You don't spend mirror finish money on the legs of the table.
But the topography isn't just about flat surfaces. It's about how flat surfaces meet. The geometry of a corner is heavily regulated too.
The intersection of two surfaces is historically the most dangerous area on any machine. The guidelines strictly state that permanently joined surfaces possessing an internal angle of less than 135 degrees must be constructed with a continuous smooth radius.
So a hard 90-degree corner is just totally forbidden. Why?
Consider the fluid dynamics of a liquid encountering a sharp 90-degree internal angle. The liquid cannot physically maintain a laminar or turbulent flow deep into the absolute vertex of that corner.
It just hits a wall.
It creates a stagnant dead zone where the fluid velocity drops to zero. Organic soil accumulates in that sharp vertex, and because the cleaning fluids also lose velocity when they hit the corner, they lack the mechanical kinetic energy to flush the soil back out.
It's like sweeping dirt into the corner of a room. The broom bristles can't quite reach the absolute point where the baseboards meet.
That's a great way to visualize it. To eliminate this, the standards replace the sharp vertex with a sweeping radius.
How big of a radius?
For poultry equipment, that internal radius must be a minimum of 3 millimeters. For the baking industry, which deals with highly viscous, sticky doughs, the standard requires a massive 1/4 inch or 6 millimeter continuous radius.
So a very gentle curve.
Yes. This sweeping curve ensures that fluid dynamics are maintained. The product is constantly swept along the curve without stagnating, and the high-velocity CIP fluids can scour the entire transitional surface without encountering a low-pressure dead zone.
Now let's talk about how the engineer actually holds the machine together. Fasteners, nuts, bolts, and machine screws. Reading through these guidelines, it becomes immediately apparent that the standards view traditional fasteners with extreme prejudice.
Fasteners are considered an absolute last resort in sanitary design.
Why are they so bad?
A standard threaded bolt with its V-shaped threads is essentially a spiral staircase composed of thousands of overlapping growth niches. The sharp root of a standard thread is physically impossible to clean.
Because it's too tight.
Capillary action draws moisture and bacteria deep into the threads where no chemical spray can ever reach. Consequently, the core principle is blunt. Fasteners are strictly prohibited in or above the product zone.
But engineering reality dictates that occasionally you simply must bolt two internal components together. If a fastener is unavoidable, what is the architectural compromise?
If the necessity of a fastener in the product zone is absolute, the engineer is forbidden from specifying standard exposed threads. They must dictate the use of an ASME 60-degree stub thread.
The ASME thread. For those trying to visualize it, this is the heavily pronounced, robust thread profile you see on a bench vise or a heavy-duty C-clamp. It doesn't have the sharp, biting V profile of a drywall screw. The threads are wider, shallower, and have flat trapezoidal peaks and valleys.
That open profile is the key. The ASME 60-degree stub thread lacks the sharp microscopic root vertex of a standard machine screw.
So the liquids can actually get in there.
Because the valley between the threads is open, wide, and shallow, the surface tension of the cleaning fluids is broken, allowing the chemicals to physically flow into the thread profile and wash away the contaminants.
But I must emphasize, even the ASME thread is viewed as a necessary evil.
Oh, absolutely. The overriding preference is always to permanently weld the components and grind the joint perfectly flush to that 1.8 micron mirror finish.
Okay, this brings us to a conflict in the guidelines that I find incredibly compelling. It is the paradox of the part number.
Yes. The part number problem.
On one hand, we have spent 20 minutes detailing the obsessive requirement for perfectly smooth 1.8 micron surfaces devoid of any microscopic crevices. On the other hand, the reality of industrial maintenance dictates that a mechanic needs to know what specific part they are replacing. They need a part number.
And you cannot use an adhesive paper sticker. It will disintegrate in the CIP cycle and contaminate the food.
Right. You have to put the number directly on the metal. How do you mark the metal without creating a bacterial sanctuary?
It is a profound contradiction, and the standards enforce a very specific hierarchy of solutions to navigate it. The primary directive is geographical. Whenever physically possible, the engineer must dictate that the part number be placed on a surface located within the non-product zone.
Put it on the underside or the external face of the component, far away from the food stream.
Exactly.
But consider a component like a solid stainless steel mixing paddle or a dough extrusion die where the entire object is submerged in the product zone. There is no non-product surface available.
In that unavoidable scenario, the standard dictates the exact mechanical process for marking the metal. If the number must reside in the product zone, it must be engraved or electrochemically etched at the absolute minimum readable depth. The guideline explicitly outlaws the traditional method of stamping the number.
Why is a steel stamp worse than an engraving tool? They both leave an indentation in the metal.
The difference lies in how the metal is physically displaced. When you strike metal with a hardened steel alphanumeric stamp, you are applying immense physical trauma.
You're smashing it.
Exactly. The metal does not vanish. It is violently displaced laterally and upward. This action creates a deep, jagged crater surrounded by raised, overlapping microscopic lips and stress fractures around the perimeter of the number.
So you are essentially building a miniature mountain range of overlapping crevices.
The perfect, uncleanable hiding spot for pathogens.
It folds the metal over on itself.
Yes. Engraving, or better yet, electrochemical etching, operates on a completely different physical principle. When performed at a minimal depth, these processes cleanly remove or vaporize the material without inducing structural trauma to the surrounding area.
So no jagged edges.
They do not create raised lips or microscopic folds. They leave a shallow, smooth depression that, while technically a disruption of the surface, can still be effectively penetrated and scoured by the fluid dynamics of the cleaning cycle.
The level of microscopic control required here is astounding. Every physical interaction with the metal is policed. And this leads us to the larger architectural structures, specifically addressing hollow spaces. The terminology used in the guidelines is severe. They declare an all-out war on the concept of the dead end. What constitutes a dead end in a sanitary fluid system?
A dead end is the ultimate architectural failure. It is officially defined as an area, cavity, or space wherein a product, an ingredient, a cleaning agent, or any extraneous matter may become trapped, retained, or not completely displaced during normal operational flow or sanitation procedures.
It is a blind alley in the plumbing. Fluid enters under pressure, but there's no exit flow to flush it back out.
Exactly. The fluid velocity drops to zero, the chemicals stagnate, the temperature drops, and it immediately becomes a guaranteed, highly productive growth niche.
So how do they eradicate them?
To eradicate dead ends, the engineering standards aggressively attack the use of hollow spaces. Imagine the primary structural frame of a massive conveyor system. An engineer will typically specify square steel tubing because it offers excellent structural rigidity while minimizing weight and material costs.
But by definition, square tubing is hollow inside.
And that hollow interior is a massive, dark, uncleanable void, just waiting to become a biological hazard. Therefore, the standards dictate that all hollow areas of equipment, including structural frames and rotating rollers, must be permanently hermetically sealed.
You can't just tap a plastic end cap into the tube with a mallet.
Absolutely not. The ends must be continuously welded shut, sealing the hollow void from the atmosphere forever.
But the complication arises when you need to attach components to that hollow frame. If an engineer dictates that a motor bracket or a junction box should be mounted by drilling a hole through the wall of that square tubing and tapping threads into it, they have compromised the hermetic seal.
Because even with a bolt threaded tightly into that hole, the microscopic gaps in the threads will eventually allow liquids to seep past.
The thermal cycling of the machine heating up during production and cooling down at night will literally create a vacuum effect, sucking moisture and organic matter past the threads and deep into the dark, uncleanable interior of the tube.
And the frame will silently harbor a massive bacterial colony, rotting from the inside out.
Precisely. To prevent this, the standard mandates that anything attached to a hollow frame studs, mounting plates, brackets, even the metal nameplates, must be continuously welded to the exterior surface. You cannot breach the wall of the tubing.
Continuous welding is key here. You can't use skip welding, where you weld an inch, leave a gap, and weld another inch.
Skip welding leaves gaps where moisture can slide behind the bracket.
It must be a continuous, unbroken 360-degree weld, ground smooth. The same rigorous logic applies to rotating members. Drive sprockets, belt pulleys, and agitator shafts are required to be completely solid metal.
But what if they have to be hollow to save weight?
If an engineer determines they must be hollow to reduce rotational mass, they must be fully hermetically sealed with continuous welds. However, the standards implement a brilliant secondary failsafe for hollow rotating parts. Before the final weld is closed, the hollow interior must be injected with a highly visible liquid dye.
The dye test. This is an incredibly elegant solution to a microscopic problem. I assume this acts as a passive diagnostic tool.
It acts as an immediate visual alarm system. The continuous weld sealing that hollow roller is subjected to immense operational stress vibration, torque, and thermal expansion over thousands of hours.
And welds can fail.
If a microscopic fatigue fracture develops in that weld, it might be entirely invisible to the naked eye of the maintenance crew. Without the dye, that hairline fracture would silently begin drawing in moisture and bacteria, turning the interior of the roller into a spinning centrifuge of contamination.
But with the dye inside, the moment that microscopic crack forms, the centrifugal force of the spinning roller drives the brightly colored dye out through the fracture.
It creates a massive, highly visible stain on the exterior of the equipment. It entirely removes the burden of microscopic inspection from the maintenance crew,
The machine physically bleeds to signal that its hermetic integrity has been compromised.
allowing the operators to halt the line and replace the part before a contamination event can occur.
That is diagnostic engineering at its finest. But speaking of rotating parts, we have to address the ultimate vulnerability, the penetration of a tank wall. You can completely seal a hollow roller, but what happens when a solid rotating drive shaft from an external motor has to pass through the steel wall of a vat to turn the mixing blades inside?
You cannot weld a spinning shaft to a stationary wall.
Right. You must use a mechanical seal.
Mechanical seals are arguably the most heavily scrutinized engineered components in sanitary design. They represent a deliberate, necessary breach in the physical containment of the product zone. The seal is at a constant threat from two directions. It must prevent the food product from leaking out under pressure, and it must absolutely prevent non-sanitary lubricants, atmospheric air, or environmental contaminants from leaking in.
And these aren't simple rubber O-rings. We are talking about complex, precision-machined faces practically against each other, often utilizing a liquid barrier fluid injected between the seal faces to maintain pressure, provide lubrication, and dissipate the immense frictional heat.
Yes. But if that mechanical seal is located directly in the product zone, the barrier fluid itself represents a massive liability. It is one microscopic seal failure away from mixing directly into the food product.
So how do they mitigate that?
Consequently, the standards enforce a dual-layered defense. First, any barrier fluid utilized in a sanitary mechanical seal must be a non-toxic FDA-approved substance, such as food-grade mineral oil or even sterile water.
But the standards acknowledge that even a food-grade fluid isn't supposed to be an ingredient in the product. It still constitutes contamination.
Which triggers the second layer of defense. The engineering blueprint must incorporate a highly sensitive contamination detection system integrated directly into the barrier fluid loop.
What is it looking for?
This sensor array constantly monitors the pressure, conductivity, and flow rate of the barrier fluid. If the internal product pressure spikes and forces food into the barrier fluid, or if the barrier fluid pressure drops and leaks into the product, the physical properties of the fluid instantly change.
And the sensors detect that anomaly.
The sensors detect the anomaly in milliseconds, and they are hardwired to the main control logic of the facility. The system does not merely trigger a warning light for an operator to notice. It is programmed to immediately and automatically cut power to the operating equipment.
So it just kills the whole line.
The massive processing line physically shuts itself down, neutralizing the pressure and halting the flow of product before a microscopic seal failure can cascade into a multi-ton contamination disaster.
So we have traced this journey from a highly regulated 5-letter abbreviation on a digital schematic through the fluid dynamics of a CIP cleaning cycle into the electrochemical reactions of dissimilar metals, and finally to automated sensors shutting down a facility to prevent a biological catastrophe.
It's quite the journey.
The final question is one of accountability. How does a manufacturing facility ever actually prove that they executed all of this correctly? How do they prove to a regulatory body that the abbreviation SST on page 42 of the CAD drawing actually materialized as a continuous 3mm radius weld on the factory floor?
Accountability is established through a massive, meticulously maintained paper trail. This culminates in what is known as the EDTCF, the Engineering, Design, and Technical Construction File. The ultimate proof of concept. What does this file actually contain? The EDTCF is the living legal bridge connecting the theoretical blueprint to the physical reality of the machine. The standards explicitly define its required contents. It contains the exhaustive bills of material, proving exactly what components were ordered.
So no substituting cheaper parts.
Exactly. It houses the certified material test reports from the metal foundries, legally proving that the steel utilized is the specified corrosion-resistant grade and not a highly reactive substitute. It holds every single engineering change record, documenting exactly why and how a design was altered.
And it must contain the validation of the cleaning protocols, correct? It isn't enough for the engineer to just slap the abbreviation CIP on a manifold. They have to scientifically prove that the manifold can actually be cleaned in place.
Absolutely. The EDTCF must house laboratory reports and documentation demonstrating that the manufacturer physically tested the specific geometric design.
Like real-world tests.
Yes. They must provide data showing that they flowed the exact chemical concentrations at the exact specified velocities through the system and utilized microbiological swabbing to validate that the CIP process successfully eradicated pathogens from every internal surface and radius.
Once this massive file is compiled, who actually reviews it? Does the industry just operate on the honor system and take the manufacturer's word for it?
The industry relies on two distinct paths to verification, both outlined in the standards. The first path is self-certification. A manufacturer can register their company with the governing committee, thoroughly review the engineering standards internally, and execute a legally binding application warranting that their equipment fully conforms to all the criteria.
And then what?
Upon doing so, they are granted permission to display the basic certified symbol on their machinery.
That seems risky. They're essentially staking their entire corporate reputation and opening themselves up to catastrophic legal liability based entirely on their own internal audit. If I am a massive food producer purchasing a $10 million processing line, I might require a higher level of assurance before I integrate that machine into my facility.
That requirement drives the second, much more rigorous path: third-party verification. In this scenario, the manufacturer hires an independent, standardized, and highly accredited testing agency to physically invade their factory and inspect the completed equipment.
The auditors arrive.
The auditors arrive, and they systematically cross-reference the theoretical claims in the EDTCF against the physical reality of the machine. They utilize specialized tools to measure the microscopic surface roughness, ensuring it meets the 1.8 micron standard.
They check everything.
They physically measure the continuous internal radii to confirm they achieve the required dimensions. They review the metallurgical certificates and inspect the hermetic seals. Only equipment that successfully survives this exhaustive, independent third-party inspection is granted the legal right to display the elevated, highly coveted symbol, certified third-party verified.
Which brings us full circle. What does all of this mean for the student engineer or the junior drafter who is listening to this deep dive right now? It means that the rigid, seemingly arbitrary rules governing how we abbreviate technical terms are not just bureaucratic red tape. The gauntlet of the five-letter rule, the absolute prohibition against splitting up composite abbreviations like SST, the draconian syntax rules that strip away all grammatical inflection, none of this was designed by an angry professor to make your life difficult.
No, absolutely not. These rules constitute the absolute non-negotiable foundation of a shared, unambiguous technical language. When that highly precise language is deployed to architect massive, complex, multi-million-dollar manufacturing systems, ultimate clarity is not a luxury. It is a necessity.
Because the stakes are so high.
That clarity directly prevents electrochemical corrosion. It prevents the formation of microbial growth niches. It protects the health of millions of consumers. It ensures that the massive financial investment in the machinery is not squandered because a careless design made the equipment physically impossible to clean or maintain. The line of causality connecting a sloppy, ambiguous abbreviation on a CAD screen to a lethal biological hazard in the food supply is shockingly, terrifyingly direct.
It is a profound, heavy responsibility. And as we wrap up, it leaves me with a final, provocative thought to consider. We're currently accelerating into a new era of engineering. We have fully automated parametric 3D modeling. We are integrating AI-generated schematics and augmented reality into the manufacturing process. We are designing on digital vector-based canvases where physical space is essentially infinite. You no longer have to squeeze text into a tiny 2-inch title block on a physical piece of paper. You can zoom in infinitely on a high-resolution monitor. So as the physical constraints of space entirely disappear, will the art of the technical abbreviation survive?
That's a great question.
Or will we eventually pivot back to a system where we allow the software to automatically spell every single word out in full, completely eradicating the human risk of ever misinterpreting a 3-letter code? It is something to seriously think about the next time you hit the text tool in your modeling software and try to save a fraction of a second by cutting a word in half.
It is a fascinating question regarding the evolution of our tools. But whether the instructions are rendered in abbreviated shorthand or fully articulated prose, the fundamental demand for absolute, uncompromising clarity will remain the bedrock of the profession.
Waste is inevitable. Excuses are optional. Build better next time.